welcome to the first session this morning. My name is Sascha Hauer, and I work as an embedded Linux engineer of electronics in, I think, 2004 now. Today, I don't want to talk about the kernel very much, but about Barebox, the bootloader I've written based on Ubuntu. What we're going to do today is, what I want to do is give a tour through Barebox, hot topic these days, device tree, and some future directions that will be multi-platform bootloader, and last but not least, you should see something in the Barebox library. Our tour starts with basic hardware instrumentation, startup. Of course, Barebox has a user interface, and bootloader should also start the operating system, updating the system, and bootloader is also a debugging interface for hardware bring-up. So, what does a bootloader need? The motivation for me to write Barebox is that I think the bootloader should be configurable, should be scriptable, maintainable code base is very important for me because I don't want to write code each time new I have to use it. I want the driver model to be able to reuse the drivers better. Have real file system support, that is mount file systems, copy files, and stuff like that. And it should not require the people to use the memory, to know the memory layout of the board. According to file system support, should want to be able to see every type of device as a file. That should be normal to Linux users. Unfortunately, it's not for bootloader users. And starting second stage is also a nice thing to have for debugging. So the name. It's named after VisiBox, which claims to be the Swiss Army knife of embedded Linux. And I want to show you why I think Barebox, the Swiss Army knife of bare metal, was a good name to choose. So Barebox started in 2007, based on Ubuntu 1.2. The reactions on the Ubuntu mailing list, the original plans were converted back into Ubuntu, but the reactions on the mailing list weren't exactly that enthusiastic. And so the project renamed itself to Barebox in December 2009. Since then, it evolved with approximately 140 commits per month, with support for 29 boards spread around 8 architectures, with ARM being by far the most active one. Barebox is configurable. You use kconfig to configure itself. So with kconfig, you can basically configure Barebox from a simple SRAM config, which is able to run in 56 kilobyte of SRAM to a full-blown Barebox, which is 350 kilobytes, without touching any code, just using kconfig. So the low level in it is with what every board starts with. It is required for it's required to set up ELCE RAM, and the low level it shouldn't do much more, just enough to get Barebox running. Ideally, this would be the only porting code, but unfortunately they're small. It's often written in assembly, which is not very maintainable, so Barebox allows to write this code in C. Barebox optionally gives the reset vector to board control. So you're free to do whatever you want from the reset vector on and just pass control to Barebox when you're done. But Barebox also has defaults for boards which do not require some board-specific setup. For the driver model and initialization, Barebox is based on many ideas from the kernel, and init calls is one of them. So if you have the idea from the kernel with early init calls, device init calls, stuff like that, it's the same in Barebox. And just like the same as in the kernel, Barebox, the board-specific code registers devices, which then get probed once the drivers initialize. And yeah, as said, it's nothing new. Everything is known from the kernel already. The only idea was to import it to the bootloader. The user interface. We have automatically, without doing anything, Barebox will start up whatever is the default for this board. But we can make this decision based on the information we get from the SOC. We have variables, so generic ways to find out the reason why we're here. That is being triggered from the watchdog or being triggered from cold start reset. So we can, due to the scripting facilities of Barebox, do whatever we have to do in such a case. The standard use case is to, being in interactive mode, fire up the console. And it's basically a shell, it's a hash. I think it's still, it's not default anymore in VisiBox, but this hash is derived from VisiBox. And indirectly derived from VisiBox, it's still from Google. Recently we gained menu support, which is that you can fire up a menu on the console. There is support for several input devices like GPIO buttons, touch buttons, and also some sensor interface drivers recently. And if you don't have the console, you will be happy about LEDs. Well, this is an example for the menu. It can be instantiated from C code, but also from shell code. It allows basically executing arbitrary commands from menu items. So for the occasional user, we can use shell for the menu, and for the experts or someone who wants to do special things, there's always a shell. Basically, what every bootloader needs to do is, at some point, build the kernel. Yes, so there comes a ton of options into play. We have tftp, and as for the network, it's usually useful for developers who want to develop the kernel, and they don't have to flash the kernel each time they fire up a new kernel. Several types of flashes, SD, MMC. There's kernel or Y-modem support for UART, USB master devices, and also some file systems like FAT. QB is not really a file system, but something like a logical volume manager for flashes. We have support for that as well. All of them have in common, including tftp and nfs, that they are accessible as files. So you don't have to think about where the hell does this file come from, you just have to copy it. Again, this is no new idea, it's basically what every operating system does. And okay, you can have it in a bootloader as well. And also you don't have to think about which image type you're going to load. Basically, Barebox has a single boot command for all known types in the ARM or PowerPC world. Can load Z images, view images, also Barebox images, and it handles device trees and init.rd files. So all these files are automatically detected, so you don't, you just use the command and don't need a decision inside the shell script what type of image do you have. It will just work. And of course, it should be fast. So in order to be fast, at least ARM needs the MMU in order to enable the data caches. So Barebox has support for this. And it's written in a totally generic way, so you don't have to have any board support for this. Just enable the kconfig switch, enable MMU, and that's it. If for some reason you find out that the MMU doesn't work, okay, switch it off again and try it first then. We have, at least for MMC SD, a block layer, which has some simple caching algorithm. It basically throws away the most unused block. So it's basically useful for fatty file systems in block devices. Another thing, you can switch the altitude time mode to 0, and still you will be able to interrupt. The screenshot below is one of the fastest I ever got for Barebox. It is about 330 milliseconds from the first instruction to shell prompt. Okay, it's obviously it's a stripped down kernel with an init run S, but still it's a regular Barebox without any optimizations. And the kernel still has networking support, stuff like that, so you would be able to continue from that point. Updating strategy is, depending on what you do, very simple. We have scripting for deciding what you want to do. And the actual update itself would only be a copy file from A to B. So that would be the building blocks for a project-specific update concept. Or command. As said, Barebox is not only a bootloader. Barebox bootloader is also the first software that will ever run on the new system. So we have a great toolbox for bringing up the system. Some examples, we have obviously commands for displaying memory, from M-copying, M-setting devices so that you can test that the devices actually run. You can show the register layout. M-copy, M-set, a bit special in the way that they do not only allow to copy real memory, but also from memory to files, or files to memory, or whatever else. So you will use M-copy to just show the content. You could copy the contents of some register file or some memory address up to the tftp server and introspect it later. You could also use it to save some GPIO moves set up, just copy it to the file server and copy it back again later. Tab completion is also very useful. It not only completes commands but also variables and devices. So if you don't know what to do, often it's enough to just tab copy enough and at least you'll see the possibilities that you have now.
It's for using.
GPIO command is basically the same as in the kernel. We have GPIO directly input, output, set value, and they work exactly like in the kernel. Next category would be dev info or IOMEM. Shows information about registered devices, base addresses, and which files in the dev file system they register. You basically see what Barebox has inside. IOMEM is nearly the same as Hedgehog IO.
With useful step without rewriting anything.
So one of the questions I'm quite often asked is, how big is the binary? It's really hard to say because it greatly depends on the features you compile into the binary. Some features, like for example, USB takes a certain amount of kilobytes, whereas other features like stack unwinding support, hit orphans, usually require a certain percentage of the binary. So I put the question differently: how much Barebox can we get in 128 kilobytes? All these examples are with a new feature in Barebox. It's compressed image support. So basically, this would be another full compressed image, self-extracting one. Okay, here's the example, the IMX51 damage board. You get full networking support with tftp, HTTP, PTP, and S.
Low decompression.
We don't have nor NAND flash on this board, so we only have MMC SD card, read-write. We can put the model that with an SD card or use FAT for it. So we have read and write support, stack unwinding, and very useful for debugging is KOSIMs, which will resolve the in the backtrace the function pointers into symbolic names. And we have an almost full command set, at least everything you need to be happy. Similarly, IMX28, 27 based board. There we don't need MMC cards, but instead NOR and NAND flash. Also,
128 kilobytes the compressor. Which size are the memory footprint in core?
the compressed image size. Usually the uncompressed image size doesn't matter at all because we have gigabytes of memory nowadays, and honestly we don't know what to do with it in the bootloader. Another famous one, the GIP board. Here we need USB support and the USB network adapter, quite common, at least for debugging. The last example is not 128 kilobyte, it's 33 kilobyte. It's basically an X-loader config. Those of you who know OMAP, they usually use a small first stage bootloader, bootstrap the second one, because the first stage can only occupy, I think, 64 kilobytes of memory in SRAM. And we can configure Barebox to be an X-loader itself, and in this case with NAND, MMC, and FAT support, it occupies about 33 kilobytes, which is also a non-interactive build. There's another possibility. You don't even need to have a shell in Barebox. You can compile it away and have a completely non-interactive build. Yeah, device tree. It's normal nowadays to start the kernel using the device tree, and that's because, unlike C hardware, socks are not discoverable at runtime, so we have to have some description. Traditionally, description C code. Nowadays, the description has been put out of the kernel into the device tree. But Barebox itself still uses that description in C code. So it would be nice to have the same way of putting the description out of Barebox for Barebox as well. So the next idea would be to use the device tree for Barebox as well. If it's to be written anyway, then why not use it? So the device tree comes as some ASCII tree structure, which is then converted into a binary block. And for the kernel, it can be appended to the kernel binary, it can be passed to the binary. And for Barebox, currently these possibilities do not exist yet. But we already have code to unflatten the tree and connect the device tree with the pre-existing Barebox devices. That can be done at any stage of the boot process. So basically, Barebox has all the code to probe directly from the device tree. And whenever it finds a device that is already present, it won't probe it again. It will just connect the pointers from the device tree to the existing devices. So that's an example how IMX27 tech, the Ethernet device, would look before device tree probe and afterwards. So afterwards we just have the device node attached to this device. So that's a bit of commercial. We have now that's basically the Barebox image. At the start, at the beginning, there's always the startup code. And we have a lot of board-specific code that run the binary, and ideally, with device tree, we would only have common code, the device tree attached to the end, or passed into the binary by some other means, and have no board-specific code all around the binary. I think in this theory this won't work. There will always be board-specific code, but okay, that's another story. So in theory, we can say with the device tree we can separate the board, the code from the board data, and generally make binaries more universally usable. That means less compiling, more compile testing with a single using a binary. And by using device tree, that's how device tree polygonal started. We can reuse the same kernel for binary for different hardware areas. And of course, if we use it in Barebox, we have the same advantage for Barebox as well. So, already started with the device tree. That's a bit of future work. I'm thinking about doing that, but there's not really code for this at the moment. So the next idea would be to, if we have a universally usable binary, the only remaining port-specific code is the little green block at the beginning. So the idea is basically to move this block to the end and compile in the startup code for many boards and be able to just start up the binary second stage so that the second stage can decide, I'm on port A, so I pick out the A block from there and write it to the device. So there will be an update command which will get pointers to the binary, the device tree, and the port-specific startup code, and then it has all elements necessary to bootstrap itself to whatever boot medium there is. But as said, that's some kind of future using. I don't know if it really makes sense to compile the Barebox for INX and OMAP at the same time. It's probably more meant for hardware variants. So often enough we have variants with half a gig of SDRAM and 1 gigabyte of SDRAM. Nowadays we have to compile 2 binaries for this because we can't check the SDRAM size at the moment. And that would be the way to have some port-specific code to just put it.
How did you get to reach the ports? Because currently I use the bootloader to remember all the ports.
I said you use the second stage bootloader.
So you didn't have that port-specific first thing?
Yeah, of course.
Different ways. We have one binary,
In fact, it's
a
going
common
to
binary,
be
and
bigger.
different style code. Or you could
But it
have
looks
something on
better
the
that
both,
way.
sure,
It looks
which
better
you
that
tell,
way.
hey, I want this binary, this startup code, put this together on an SD card. And the other thing is more for updating. You already have the bootloader on your SD card. You start it up, and then you have everything to start at second stage, the new bootloader, and the new bootloader will get the information from the device tree or whatever to bootstrap itself again. Oh, I have a slide for this, which explains it better. So, yeah, it's basically the Barebox agenda which combines this usable binaries. And the Barebox update handler, as already mentioned before, could run the development host to build an SD card image, or on the Barebox itself, or maybe even under the running kernel to and of course, if we already separated the common code and the startup code, and we would call the Barebox exactly like the Linux kernel, then we could use the Linux kernel itself in the next step.
Actually, people are doing that today. I mean, there's no point. There's no point having a kind of weird operating system shim to boot a kernel. I mean, all you need is a very small IPL booting the kernel, and then you have a bootloader with kexec. That's how it works today. So what's the point?
The point is, actually, there's no problem booting one kernel, but will it be the update kernel, or will it be the regular kernel?
No, I mean the whole point is, and if you look at fast booting, you want not to have any shim layer in between the IPL and the payload kernel, the production kernel. And for update purposes, you have a fallback variant on the flash or whatever medium you can boot of. So it's not rocket science to do, and it's done today. So I really do not understand what you're heading to. I mean, you're migrating from a U-boot variant into something which resembles a kernel, and then you say FutureWork is going to boot a kernel out of the startup code. I mean, we are doing that today. So I'm not seeing the value of going through all that hoops if we can do it today already. And then, I mean, for development, and that's the whole argument about bootloaders, that development people need a bootloader because they want to tftp their kernel and then execute it. I mean, that works. kexec works on all platforms today, and if it doesn't work on a particular platform, just fix it. Instead of rewriting something you need to do anyway. I mean, as an engineer, I really hate the fact that you have to touch device drivers for two different types of software. Even if you reuse the Linux drivers in Barebox, it's still you have to maintain them separately. And it's total overkill. It's an engineering nightmare. So, and you're heading to something which is actually done by people right now. So I don't understand the transition phase you're going through.
What I wonder about is, where is this code?
I mean, it's partially in U-boot, which you forked. The IPL stuff is there. And all you need is to get this initial boot kernel out of some storage device, which usually is done either by reading it from flash or it's presented you by some means of the internal bootloader of the device itself.
Yes.
I mean, that's a matter of fact.
I know it's in U-boot, and okay, we have a different bootloader. What's the problem?
So, no, the difference is that you can use U-boot, the IPL part, as a standalone thing which bootstraps your kernel, and then you don't have a restricted shell, you don't have any restriction on any device, and the next implementation of some kind of file system thingy, you just use what you're using anyway.
Yeah, I've seen patches implementing networking support for the SPL and U-boot.
Yeah, I fundamentally hate that as well, because it's just brain dead.
I stop you in here because I believe both bootloaders can boot a Linux kernel directly from the SPL.
Pardon?
Now, both of the bootloaders can only create a thin shim that close the kernel in the SPL or whatever they call it in Barebox, and just start a kernel. So you don't have to enter the full bootloader anymore.
Yeah, but I'm still questioning the efforts, the engineering efforts on reinventing the wheel.
But sorry, isn't this a discussion that we can take afterwards? And let,
Yeah, sure.
Yeah, I think yeah.
We're almost done anyway, so. At least I want to show the demo. Okay, what I have here is Freescale IMX51 Quickstart board running Barebox. Just press reset so we can start. That's basically Barebox starting up. And what I just want to show is that we can go to the menu, select which boot entry we want to use. So first option would be just fire up the kernel from C card. I want to show is just how to add a new boot entry to the menu. So we can edit the boot entry, add a new entry, give it some name.
If it doesn't do Emacs, it's really bad.
I think you have to implement that yourself.
Yeah, but who comments do it? Support Emacs.
What I haven't mentioned here, we have automouter support, so I basically created some auto mount points in the system, so whenever mount tftp is accessed, then in the background the tftp file system is mounted. So I can just we won't do device rebooting here at the moment. That will be hit new kernel. Booting from tftp. I think we need some time. And yeah, we can manipulate. Manipulate this further. Maybe by adding some init-rd. The next step would be to just copy the very same init-rd to that file system, and you would be able to start it up from there. configured here. There's the over there, the second one, and the tftp server. This is down there, and it's another. So the directory is created, and then we run automouter command, which executes the necessary command in the background. So all we would have to do is to exchange this file. Another file. Okay. Anyway, we would, so we will be able to come down to a startup time zero. That's the second setup. Okay. Thank you very much for listening.
They have a support for PXE booting?
Pardon?
PXE boot.
PXE boot. No, we don't have that.
Okay.
I think John Christoph is working on that, and I think he has some patches, but I don't know much about PXE boot, so you would have to ask me. Any other questions? No questions? You're all running Linux now as bootloader, right?
More or less, that's the drivers. How many drivers you have?
We have MMC card drivers for Atmel, OMA, IMX. We have USB drivers, ELCE, and
What about the
Ethernet.
What about wireless? I'm serious.
There are some generic drivers, some SOC drivers. I don't know, 10, 15. I don't know how many.
You showed that you replace with Barebox the OMA start controller, but what about one controller? So Barebox should reduce 16 kilobytes.
Jean-Christophe is working on that. I don't know his exact plans, but I don't think there will be full or Barebox in that kind of space.
So
It will be one thing.
all that start controller, replacing standard 1899.
Yeah, that's, I said, that's from the south area, and I don't think he will put a, he will use the pre-bootloader mechanism we have in Barebox for that. So basically there is a kickstart which does loads Barebox. At the time, my main motivation was I wasn't happy with reboot. Yeah, there was one point in time where I broke U-boot in a way I couldn't fix it, and yeah, that was the starting point. It was broken anyway, so remove all other stuff as well.
Well, I think it's a discussion whether my bootloader is better or yours, or if you need bootloader at all, rather pointless, because I think it's open source and it's an offer. There are a lot of projects where you can use a bootloader, you can use
interesting. This fits our needs in quite a lot of projects, and we find it's a very maintainable platform. And it even works on hardware where we don't have a real support for that. It's actually quite often a use case for us. We import the install device, we don't have a code for that yet. We don't even know if the hardware works, so if it's broken, if the layout is correct or something like that. And it's rather convenient to have something without interrupts, without any complexity, things like that. And so it's just an offer, you can use whatever you want. So,
I'm not arguing that there is a value to having those different bootloaders, but still, when it's open source and we can discuss it in the open, then one of the values is there that it question approaches. So that's why I was asking about the rationale behind doing that and going through the hoops and loops to basically come to the conclusion that you want to use a kernel as a bootloader.
As you might imagine, Barebox for me is also a hobby, and I learned quite a lot about hardware. In the kernel, everything is done, so not everything, right? There's still a lot to do, but I won't go into memory management for the kernel. So, thank you very much. We're out of time.